Welcome back to Dr. Dan's channel. This is where we slow things down, zoom out, and look at what's changing beneath the surface. Not through headlines or hype, but through the deeper systems that shape power, security, and the future. Today, we're answering a deceptively simple question. What makes quantum computers so powerful? Because the real story isn't just faster computers. The real story is that quantum computing targets the structure of problems we rely on to keep modern society functioning, especially encryption, the invisible layer of trust underneath banking, government systems, medical records, cloud services, and private communication. And even though large-scale quantum computers don't exist yet, the threat they pose is already shaping national security policy, corporate cybersecurity, and the timelines of global technological competition. To understand why, we need to begin with something quietly unsettling. Right now, some nation-states and some well-resourced actors are intercepting and storing huge volumes of encrypted data. Passwords, financial transactions, corporate research, government communications. They can't read it today, so why keep it? Because they believe that within 10 to 20 years, possibly sooner, they'll have access to quantum systems capable of breaking certain forms of encryption in minutes. This strategy has a name: store now, decrypt later. And it works because some information doesn't expire quickly. Industrial designs, pharmaceutical research, intelligence sources, diplomatic cables, strategic military planning, even personal data that can be weaponized later through blackmail, identity fraud, or political pressure. So when people say quantum computers are years away, they're missing the point. If someone is collecting encrypted data today, the clock started already. And that's why major security institutions have been unusually direct about the stakes. In plain terms, a sufficiently capable quantum computer would undermine widely deployed public key cryptography, the kind that underpins the modern internet. So how did we get here? The encryption breakthrough that built the internet for most of human history. Secure communication was a logistics problem. If you wanted to exchange private information, you had to meet in person, agree on a secret key, and then use that same key to encrypt and decrypt messages. That's called symmetric encryption. It works, as long as nobody else ever gets the key. But as societies scaled, that approach hit a wall. How do you share a secret key with someone you've never met, across an insecure channel, without the key being intercepted? In the 1970s, cryptographers introduced a profound idea. What if we could encrypt messages using something that could be public, without making the secret public? That idea gave rise to public key cryptography, and one of the most famous implementations is RSA, named after Rivest, Shamir, and Adelman. The core concept is elegant. Each person privately chooses two large prime numbers, secret primes, and multiplies them together to produce a much larger number. That large number becomes public. If I want to send you an encrypted message, I use your public number to scramble it, in a way that can only be reversed if you know the original prime factors. In other words, it's easy to multiply large primes. It's incredibly hard to factor the result. That imbalance, easy one way, hard the other, is what makes RSA useful. And with classical computers, it works remarkably well. Even with the best-known classical factoring methods, using modern key sizes, the time required to factor the product of two huge primes becomes so astronomical that it's effectively impossible. We're not talking about hours or days. We're talking about timescales measured in millions of years. So RSA, and systems like it, became one of the core pillars of digital trust. And then, quantum computing entered the story. Why quantum is not just faster. Here's the first misconception we need to clear away. A quantum computer isn't just a better classical computer. It's not simply faster at everything. In fact, for most problems, a quantum computer is useless, or at least not meaningfully better. Quantum advantage appears when the problem has a specific structure that quantum mechanics can exploit, especially problems involving certain types of periodicity, interference, and probabilistic state spaces. So the real question becomes, what does quantum computing do differently? Let's talk about bits. A classical bit is either 0 or 1. 2 bits can represent 4 states, 0, 0, 0, 1, 10, 11. But crucially, a classical computer can only be in one of those states at a time. So if you want to compute something across many possible inputs, like trying many potential factors, you typically have to do it sequentially or with parallel hardware. Now enter the qubit. A qubit also has 2 states. We can label them 0 and 1, but it can exist in a superposition of both. And when you have multiple qubits, the number of possible combined states grows exponentially. With 20 qubits, you can represent over 1 million states. With 300 qubits, you can represent more states than there are particles in the observable universe. That's the headline everyone remembers. But there's a catch. And it's the catch that separates hype from reality. The catch. You can't read the superposition. If a quantum computer can represent a massive superposition, why not just compute everything at once and read the answer? Because when you measure a quantum system, the superposition collapses. You get one outcome, effectively at random, and the rest disappears. So quantum computing is not parallel computing in the normal sense. The power comes from designing algorithms that use interference to amplify the probability of correct answers while canceling wrong ones, so that when you finally measure, the right answer appears with high probability. That is extremely hard to do, and it's why there are only a handful of quantum algorithms that truly matter. But those handful hit some of the most important foundations of modern digital life. One of those algorithms is Shor's algorithm. Shor's algorithm, the encryption nightmare. In 1994, Peter Shor showed that a quantum computer could factor large integers efficiently, meaning in a time that grows reasonably with the size of the number. That is exactly what RSA security depends on being hard. So the big question becomes, how does Shor's algorithm actually do it? To understand the logic, it helps to start with a simplified classical trick, one that feels almost like a magic trick. Imagine you have a number n that is the product of 2 primes, call them p and q, and you want to factor n. You pick a random number g that doesn't share factors with n. Then you compute powers of g modulo n, meaning you compute the remainder after dividing by n. What you find is that the sequence of remainders eventually repeats. It's periodic. And critically, there exists some exponent r, such that gr is congruent to 1 modulo n. That r, the period, becomes the key to unlocking the factors of n, because with the right algebraic steps, you can turn r into candidate values that likely share factors with n, and then extract those factors using Euclid's algorithm for greatest common divisors. Here's the problem. On a classical computer, finding that period r is computationally expensive for large n, but quantum computers can find r efficiently. Why? Because quantum mechanics is unusually good at extracting periodicity, if you know how to ask the question. And this is where the quantum Fourier transform comes in. A normal Fourier transform decomposes a signal into its frequencies. If a signal is periodic, Fourier analysis reveals the frequency content. The quantum version does something related, but with quantum states. In Shor's framework, the quantum computer creates a superposition over many exponents, computes the function values in a linked, entangled way, and then performs a partial measurement that leaves the system in a superposition that is periodic. Then the quantum Fourier transform is applied, which concentrates probability around values that encode the period. You measure, you infer R, and once you have R, the rest of the factoring process becomes tractable. So Shor's algorithm isn't brute force. It's not trying every factor faster. It's exploiting deep mathematical structure using quantum mechanics, and specifically using interference patterns to pull out the periodic signal. That's the heart of why quantum computers are so powerful. They don't just compute more, they compute differently. How close are we to breaking RSA? This is where we need to be careful, because the public conversation often swings between two extremes. One side says, quantum will break everything soon. The other says, this is overblown. Quantum computers can't even run reliably. Both contain partial truths. To run Shor's algorithm at the scale required to break real-world RSA keys, like 2048-bit RSA, you need not only a large number of qubits, but qubits that can maintain coherence long enough, with error correction robust enough to run enormous circuits. And today's qubits are noisy. That means we need many physical qubits to create one logical qubit that behaves reliably. And that is the real bottleneck. Over the past decade, estimates of the required number of qubits have shifted significantly, not because the threat disappeared, but because engineering and algorithmic improvements changed the assumptions. Some paths suggest the requirement could be in the tens of millions of physical qubits for breaking RSA 2048 in a practical time frame, not thousands. And that sounds impossibly far away until you remember something important. Technologies often look impossible until they don't. The internet once looked like a niche tool for researchers. So did machine learning. So did mass deployment of smartphones. Quantum has been slower than some hype cycles promised, but progress has been steady, and in some areas, surprisingly fast. Which brings us to the geopolitical dimension. Quantum isn't just a research project. It's a strategic capability. Why governments are taking this seriously. Now, even without a cryptographically relevant quantum computer today, governments are already moving because store now, decrypt later turns the future into a present risk. That's why the US has pushed agencies toward migration planning and why standard-setting bodies have been working for years to identify cryptographic systems designed to survive a quantum world. Because if we wait until the quantum machine exists, it's already too late for the data that was stored. And cryptographic migration is slow. It's not like updating an app. Encryption lives inside banking systems, industrial control systems, embedded devices, long-life infrastructure, and legacy code nobody wants to touch. The transition is closer to replacing the plumbing of a city while the city is still functioning. So what replaces RSA and its cousins? Post-quantum cryptography. The plan after RSA. The good news is, cryptographers didn't sit still. For years, researchers have been developing and stress-testing encryption systems that appear resistant to both classical and quantum attacks. One major approach is lattice-based cryptography. The intuition can be explained with a geometric metaphor. Imagine a lattice, a structured grid of points defined by vectors. If you have a nice set of vectors, it's easy to navigate. Easy to find the closest lattice point to a target. But if you describe the same lattice using a messy set of vectors, vectors that are technically valid but awkward, navigating becomes much harder. Now scale that to hundreds or thousands of dimensions. In 1,000 dimensions, taking a step that helps in one dimension can ruin you in the other 999 dimensions. The problem that underpins many lattice systems, variants of the closest vector problem, or related constructions, becomes extremely hard. Crucially, as far as we know, it stays hard for quantum computers too. So the emerging strategy is move away from public key systems vulnerable to Shor's algorithm. Deploy post-quantum schemes, often lattice-based, that appear resilient. Do it early enough that store now, decrypt later becomes less effective. This is why post-quantum cryptography isn't some abstract academic topic. It's operational. It's the quiet work of preventing a future security rupture. And it's happening behind the scenes, led by cryptographers, standards bodies, and engineers who rarely get public attention. The kind of people you only notice when something breaks. The new reality. Two races at once. Here's the deeper structural point. We're now in two races simultaneously. Race 1, building quantum computers that can perform useful, reliable, large-scale computation, including potentially breaking legacy cryptography. Race 2, migrating the world to cryptographic standards that remain safe even if that quantum computer arrives. And those races don't need to end at the same time for serious consequences to occur. If quantum capability arrives before migration is complete, the world faces a period of asymmetric vulnerability, where some actors can decrypt what others still think is safe. That's not just a cybersecurity problem. That's a power problem. Because the moment you can silently read encrypted communications at scale, you don't just gain information, you gain leverage. So what makes quantum computers so powerful? If we pull everything together, the answer is this. Quantum computers are powerful because they can exploit the mathematical structure of specific problems using quantum mechanics, especially superposition, entanglement, and interference, to do things that are effectively impossible for classical machines. Not across all tasks, but across certain foundational tasks. And unfortunately, some of those tasks sit at the core of modern digital security. At the same time, the story is not fatalistic. We're not helpless. The world is already responding through post-quantum cryptography, migration planning, and standards. But this transition is one of those rare moments where the future arrives unevenly. Some institutions will adapt early, some will adapt late, some will only adapt after a breach forces them to, and the consequences will fall along those fault lines. Because encryption isn't just mathematics, it's trust, encoded. And quantum computing is forcing us to rebuild trust at the level of first principles. Which is why this matters now, not when the first cryptographically relevant quantum computer finally turns on, but today while the migration window is still open. If you found this analysis useful, subscribe to Dr. Dan's channel for clear, in-depth breakdowns of the forces shaping our world. Like the video if it helped your thinking, and share it with someone who values depth over noise.